Oh no, he's an adult.
Terrifying. Very, very scary. I will begin. Ahem. Ahem. Hem. Ahem. I'm gonna have to separate you guys. See here. Dear Heavenly Father, we thank you for this day. I thank you for the students and their exuberance. Help us to cover what we need to today, to glorify you in the process, and just help the students as they prepare for their test in here to do their best, Lord. In your name I pray, Lord Jesus. Amen. Okay, so first things first, let me talk about the problem I got stumped on last class. So, I think, so I talked to a few different people about this, and I was able to convince some people into my my ridiculous conviction that it wasn't sliding, because it definitely is sliding. So here we had 3m, over here we had m1, 3m was m2, this was 50 degrees, and over here was 30 degrees, and I had that the coefficient of static friction was 0.8, the coefficient of kinetic friction was 0.4, I believe. Is that right? Okay. Now, and then I did things like, you know, there's a pulley here, right? And you've got the rope connecting these like so. And so what I want to share with you, I think the right logical process here is to start, if there's an if you're not sure if it's moving or not, right? Then like, I think the right way to think about these is to just decide whether or not it's possible for them to just sit there with no tension at all. All right? And so I'm going to explain how to go from that point to just kind of systematically go through it. So I'll start with the 50-degree side, right? On the 50-degree side, we have, whoa, started rolling. You got yourself, let's see here, like this force of gravity is 3m g sine 50. Then what else you got going on here? You've got the tension force like that, and you've got the friction force on 2 like that, right? Over here, you've got the tension force, and down this way you've got g sine 30, right? And what else do you got? You got friction force potentially like this. All right. Now, I'm still assuming that the direction for positive acceleration is like that, because that seems like the natural thing to do in terms of this is the heavier box on the steeper incline, so certainly that if the motion's any which way, it's going to go to the right, yeah? Now, so my introductory thought is, does box 2 slide? All right? And so if we look at box 2, we've got you know, M2A, which by the way is 3MA, equals to what? Well, 3mg sine of 50 minus the tension minus the force of friction on 2, all right? And on the other hand, we've got M1A, which is just MA, is equal to what? Well, the tension minus mg sine 30 minus the force of friction on 1. All right. What else do we know? Well, we know that the force of friction on 1 is less than or equal to mu sub s, right? Times the normal force on 1. What is the normal force on 1? Well, that is, so 0.8. And as we talked about last time, the normal force is just from this, right? This other piece here, mg cosine 30. So we've got 0.8 times mg cosine 30. All right? And the force of friction from 2 is less than or equal to mu sub s times the normal force on 2, which is 0.8 times m, not mg this time, but 3mg. cosine 50. All right? So those right there, right what we're looking at, these are the maximum possible forces of friction. All right? So this is a setup. So let's just focus our attention on box 2 to start with, because that's the heavier, that's the one that's just going to slide on its own volition. All right? So like if you just look at box 2 on its lonesome, just sitting there, right? What's going on? You've got, you know, the force, you get your 3 mg sine 50 down. And what's opposing that motion downward? Well, if the rope's not attached, just for a second, suppose the rope's not attached, yeah? Then you've got the force of friction this way, yeah? And if that's going to be in equilibrium, well, so that's all that's at play. In order to get equilibrium, you'd have to have what? You'd have to have the force of friction 2 equals to 3 mg sine 50. Is that true? Well, I don't think that's possible. So this works out to what? What's that value? Well, if you crunch the numbers, 3 mg sine 50 is equal to, where'd that thing go? Ah, there it is. That is 2.298 mg. All right, that's 3 mg sine 50. In contrast, what's the maximum force of friction? Remember, it's less than or equal to 0.8 times 3 mg cosine 50. What's that? That works out to 1.54 mg. Okay? So that's the maximum force of friction that's available for mass 2, and that means it's not going to stay put, right? In principle, it wouldn't stay put. But what could keep it from sliding? What would you need to keep it from sliding? So we need, you know, if you look back here at Newton's law right? You've got this term right here, which is what? 2.298 mg, we just calculated it. And this right here is at most 1.54 mg, right? So in order to get this to balance out to 0, you have to make up the difference where? You have to, yeah, tension has to supply the rest of the force. Well, let's calculate that. What is 3 mg? What is 3 mg, you know, sine 50 minus, you know, max friction on 2? The difference of those two numbers, right? 2.298 minus that, which gives me 0.76 mg. All right? So that, let's keep this number in mind. This is the tension we need to stay at rest, right? That is the amount of tension you need if you're maxing out your friction on M2, all right? Certainly you could have more tension than that, then the friction on M2 would be less, but let's just, for exceptional case, let's think about that. That's the maximum, that's the minimum tension we need to keep M2 from sliding down the plane, right? Now how about, let's think about M1. Let's think about M1. M1, on the other hand, well, it's doing better, right? Because it's at 30 degrees, yeah? And so you've got, you know, mg sine 30 acting down, and you got the force of friction acting up, right? Force of friction 1. And this is less than or equal to mg, mu sub s, mg cosine 30, right? So if we look at that, what's the max force of friction on 1? Maybe I should just put the number in over here. So the max force of friction on 1 works out to what? What's 0.8 times mg cosine 30? That works out to 0.693 mg. All right? Now, great. What is, so that's how much friction force is available to M1 given the interface. And what's mg sine 30 equal to? That's 0.5 mg, right? So since 0.5 mg is less than, F friction 1 max, which is, by the way, 0.693, what would that mean? That would mean that ignoring the pulley and the rope, just setting that box on its lonesome, it would just sit there. The force of friction would hold it in place, all right? What force of friction would be on it? Not 0.693 mg, but 0.5 mg, right? Because the static force of friction goes from 0 up to the max, so it's adjustable. That's what makes these problems complicated, right? So what does that mean? What's the maximum tension? What's the maximum tension then available from the friction force that's left over here on box 1? What's this say maximum tension available before M1 starts sliding? What would it be? Can you see it? So this is Newton's law for M1, right here, right? So for this to be 0, I have what? I've got my tension, and then I've got mg sine 30, and I've got this force of friction, right? So the biggest this force of friction can be is what was it? Do I have those in the right direction? Just a second here. Oh, I think my, do you guys think that's wrong? No, it's not wrong. I was thinking about the direction. Is it right? I think it's right. So anyway, what I get then is that we have at most 0.693 minus 0.5 mg, which is 0.193 mg for tension. That's the maximum tension that we can generate before M1 slides. Is that enough to keep M2 from sliding? What was necessary for M2? For M2, we need a tension of at least 0.76 mg, right? So that's about 0.5 more than the friction force allows. Therefore, it's sliding. We're in the kinetic regime. Does that make sense? There's just not enough friction force to keep it in place. So I think this is the kind of logic that you have to go through to solve these problems. And obviously, it's much easier to solve if there's just one mass, right, as opposed to two. But now that it's sliding, how do you solve it? So we figured out it's sliding. What's that mean? Let's finish the problem. Therefore, it's sliding. So what does that mean? Both of the forces of friction are what? Kinetic, right? So that means that the force of friction 1 is actually equal to what? Mu sub k times the normal force. No longer less than or equal to. Kinetic is constant. It's easy. Equal to mu sub k times the normal force. Instead of the 0.8, we have, it's given to be 0.4, right? And then you can plug that in up into here and solve it. So, I mean, we can do that, I suppose. If I add these two equations, what do I get? Adding the two equations gives me 4ma is equal to, 3 mg sine 50 minus force of friction 2 minus mg sine 30. We already know a lot of these numbers, but I'm just writing them down. Minus the force of friction 1, right? So the acceleration then, and keep in mind that this is what? This is we just wrote it here, 0.4 mg cosine 30. And the other one's 0.3. Oh, excuse me, that's bad. That was on 2, right? On 2 is the one with 0.43 mg cosine 50. My bad. 0.4 times 3 mg cosine 50. And this one here is 0.4 times mg cosine 30. All right. So notice finally, there's an m everywhere. Here, 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 and here. So we actually didn't need to know the mass. It cancels out, right? And we get acceleration is, in fact, 3 sine 50 minus 0.4 times 3 cosine 50 minus 0.5, that's sine of 30, minus 0.4 times the cosine of 30. And that's all divided by 4. And that gets multiplied by, factored out, a g. And so there you go. The acceleration is equal to whatever that is. So, come on. Oh man. Here it is. Let's see here. Where'd my calculator go? Well, did you guys figure that number out for me? So I got 0.17 times g, which is about 1.67 meters per second squared. There you go. Professor always works problems easier in class than in the homework. Not true. This happened, right? You're like, well, that problem wasn't that hard if you didn't get confused on it. That's true also, right? So if we hadn't spun our wheels on that last time, it wouldn't have seemed so hard. And if it's any consolation, I managed to trick some other people into thinking it was stuck too. They bought into my confusion. So, and then I let my wife work on it for a little bit, and she's like, no, it's moving. And I'm like, all right, it's moving. If Ginny says it's moving, it's moving. So anyway. Okay, so any questions, you guys? Rest of the time is yours. So you're like, then we'll leave. No, go on. What's the test going to look like? Oh, I don't know. That's a good question. I would say it would look like. So, this right here, by the way, is an easier version of the problem we were just looking at. So this is from something called, I think I can post, I'll post this for you. If you're interested, I'll post this in Canvas. This is what I call a workshop. We used to have physics set up so that, you guys have like 8 labs. I used to take the other like 7 labs or like 6 of them and run a quote unquote workshop, which is basically like a 2-hour problem session. That just doesn't make sense anymore because of the way the labs are run, unfortunately. But this is what that's from. I called them workshops. They're basically like labs, except where you learn things. Oh, I'm sorry. Did I say that? Sorry. I misbehave. So I will post this. I will post this in the Canvas when I remember. But I would point out this is an easier version. What makes this easier is there's no friction, right? So you just have to sort out, the part of gravity parallel to the plane, and there it is. Okay, you asked me what the test looks like. Here, I'll show you one from yesteryear. Why not? Let's see here. What happened to Physics 231 of 2012? What happened? What did I do to them? Let's see here. Problem 1. Skydiver with mass 70 kilograms has a drag force of BV squared and a terminal velocity of 30 meters per second. What's the value of the drag coefficient? So there's one. Here, you're given the velocity as a function of time. Find the position and acceleration. So you differentiate to find the acceleration, you integrate and fit the initial condition to find the position, right? So there's that. Let's see here, what's up next? A toy gun has a muzzle speed of 13 meters per second. What's the maximum range on level ground? So that's a pretty, max range formula problem. Remote control with mass 1.2 kilogram travels in a circle of radius 2 meters at a constant speed of 2 meters per second. What's the force of friction needed to maintain this motion? That. So these have all been like gifts, right? Every last one of these is a gift. Yes? These are gifts. We're starting to find an actual problem. Here's one. So you have two ice blocks, mass 1 and 2, slide across a frictionless surface. They're pushed by a horizontal force with magnitude m1 plus m2 times g. What's the acceleration of the system? So, So that one's, you have to think algebraically, right? There aren't numbers. So you have to write down Newton's laws and think through it and so forth, but you strike a baseball bat 1 meter above the ground such that the ball leaves the bat at 15 meters per second. The ball travels 10 meters horizontally before striking the ground. Then at what theta was the ball hit? This may look familiar as I have recycled it on your mission. So, yes, this problem is not as easy, right? Here we actually have to sort through the kinematic equations. We have constant velocity in the x, depending on the angle at which it's hit, right? And we have the velocity in the y, of course, is always, decelerating by 9.8 meters per second squared. And then algebra. And a quadratic equation in tangent theta as it happens. 6.9 degrees. I don't know if I kept the numbers exactly the same for you guys. I can't remember. Here's another one. You push a box with the force of 100 newtons directed 60 degrees above the horizontal. The box accelerates at 2 meters per second squared across a plane with coefficient of kinetic friction 0.5. Then what's the mass of the box? So we have to draw the free body diagram. We have to break that pushing force into its pieces, right? You've got the 100 newtons cosine 60 part of it, and trying to find my laser. Aw, man. Oh, over here. Now, Professor Dromby has told me that I could avoid this problem by, instead of just making up problems on the fly, just working problems out of books. But I said that that's very uninteresting and, seems way too easy. So I think it's more fun to just think of a problem and try it sometimes, It's a sense of adventure. So, and by the way, this seemed like such a simple problem, didn't it? Like this one we spent a half hour on. But anyway, so here, this 100 newtons cosine 60, that's the horizontal part of this force. On the other hand, the vertical part is 100 newtons sine 60, right? And why is it down? because it's pushing down, right? So that puts this down. If the angle was different, then maybe the part of the force could be pushing up, right? You have to think through it, whether it's up or down. But what I'm doing is I'm decomposing all of the forces at play into two perpendicular directions, which then we can do the analysis on, right? In this case, horizontal and vertical. In the inclined plane place, we always do perpendicular and parallel to the plane, right? That's pretty much, I think, what we've done, except for the three-dimensional problems, which are another thing. But anyway, then I write down Newton's equations, right? 0 because it's not going off the plane, and do the algebra and get to that. So let's see here. Let's continue our tour of what happened to the physics students of 2012 when you were 9, 8, 11, 10, I don't know. 8. Simpler times, right? Okay, so funny thing though, same physics, right? Same physics. Let's see here. So suppose inclined plane, coefficient static friction 0.8, kinetic friction 0.2, mass is connected to a mass, rope over pulley, find the acceleration if the angle's that, find the acceleration if the angle's that. Probably what I was trying to do with these two choices is to make one of them static and one of them kinetic. I don't know if I succeeded or not. Sometimes let's see what happened here. Are we in equilibrium part A? So I have the tension, let's see here, 0.5. Well, tension is definitely 0.5 mg. That's easier here, right? See, there's no debate over what there's no interplay here between the friction force and the tension like in the problem we started with today, right? It's way easier. The tension's 1.5 mg, right? That's what it is. And assuming that it's in equilibrium, right? If it's accelerating, the tension doesn't have to be that, does it? Because what's true is that mass times acceleration is equal to 0.5 mg minus the tension, if I'm counting acceleration to the right of the system or down of the block as positive. But anyway, equilibrium, like I said, and I get this. I get 0.326 is less than 0.7. So this is the max force of friction. And so, yeah, apparently, for 10 degrees, yes, we have enough friction. But for for 50 degrees, no, I don't know what happened here. Oh, next. The non-friction force goes down the plane, I say. Oh, man. In both cases, it's 0. So this blew up in my face. Don't worry. If I do this problem on your test, I'll have thought through it to make both cases interesting. But all right. Let's see here. Here's a mass hanging on 2 cables. Tension problem. What do you got to do? You got to break the tensions into their horizontal and vertical pieces with the appropriate angles, right? If it's 50 here, it's 40 there. So 30 here gives 30 there. There's an asymmetry there. Why is that? Because this angle is given off the vertical, and this angle is given off the horizontal. They're different kinds of angles, right? And anyway, this gives us the conditions for equilibrium, and you can work it out. Let's see here. Going on with our tour down memory lane here. Work 1 of the following. Show projectiles launched at angle theta off a building of height, speed v naught. Show that the speed vf with which the projectile hits the ground is independent of the launch angle. And then here's the 2 stones that dropped off a cliff problem. I think I actually talked about this one with you guys. I don't think we've covered problem 10a in class yet, but it is a reasonable problem to ask you. So I think that answers your question. This is, Now your test will look different because I used Microsoft Word to put that test together. I'm using something else now. So formatting wise, it'll look a little bit different. And I don't know, yours might be longer, possibly. I don't know, but that's ballpark. So there's like a little bit of easy problems, right? So you can just do those, and then ones that require algebra and analysis. Yeah.
Was this test with the same time limit we now have with 50 minutes?
I think so. But that's a good question. I'm not sure. It seems possible. I think so. Let's see here. Yeah, it was on a Monday. Hey, February 20th. What do you know? Is that yours? No, you're not. February 20th is. Oh, that's the day that my first half of your homework is due in my Calculus 2 class. Yes.
Will this cover the material on all 3 missions or just the first 2?
All 3 missions. Yep.
So will we have our graded 3rd mission?
You will not have your graded 3 mission back, which is why I told you guys to take pictures of it, so that you can look at it, the solution. So, yep. Yes, sir.
And these tests are linked on your website?
No. I mean, there are tests. Well, there might. I don't know. Maybe.
I've seen them.
You've seen them? Oh, okay. So I already put them there. Let's see here. Oh yeah, look at that. Test 1 of 2012. I actually do have them already posted on my website. I forgot about that. Wait a minute. Does that mean some of your missions have already been sitting there solved on my website the whole time? I guess it does mean that, huh?
Yeah.
I guess that would have been useful to tell you like 3 weeks ago, huh? Sorry. Actually, no, because the point is, if you don't try it, you won't learn it, right? If I just tell you the answers, that doesn't make you learn, does it? Okay, so the solution to mission 3 is posted now, by the way. So if I can find it. Where is it? Where are we? Are there any questions about the missions with that? You guys have, it's like here, I think this should be available now. I set it to post at 2:10, did it not? Yeah.
Along with like the missions, I think it was the 3rd to last one or something, the one about contact force between 3 blocks. My biggest question, I guess, about it is when we try to figure out like the contact force and all.
Yeah.
Because when we did it in class, it was with 2 blocks, and it was like a force of 2 on 1.
Yes.
When we do of 3 blocks, would it be the force of 3 to both on 1?
So yeah, here it is. For 3 blocks, here's the free body diagrams on the first one. You've got the contact force of 1 on 2, the 1-2 contact force to the left, the pushing force to the right. Then the middle block, you've got the block 1 pushing on block 2, but you've also got block 3 pushing back, right? There's no external force on that. It's just the force of the other 2 blocks pushing. And then for mass 3, well, you've just got the contact force of 2 on 3. So that's it. And so there you go. Those are your Newton's laws for the 3 masses, and then